So I know this is a fairly diverse audience from what I'm told. So there's going to be a little bit of introductory material at the beginning, but I'm going to go really fast because I want to get to the sort of the main part of the talk and the main point. I should say that a lot of what I'm going to talk about is derived from this this paper that I posted a few months ago on Open Review. It's called A Path Towards Autonomous Machine Intelligence, and you can make comments if you don't like it, which is the advantage of this Open Review. It's a relatively long paper, but it's written in a way that should make it relatively easy to read by people from sort of wide backgrounds. So not just machine learning, but neuroscience in particular, and cognitive science, and theoretical neuroscience. So okay, first thing, machine learning today sucks. At least it sucks compared to humans and animals. Clearly, we observe humans and animals being able to learn new tasks extremely quickly with very little data, very little interaction with the world. And we can do this with our machines today. We require a lot of data in supervised learning, a lot of trials in reinforcement learning. And so we're missing something big, which is seems to be taking place in animal and human learning that we are not apparently reproducing properly in machines. And as a result, machines, it's been a sort of a constant question in AI for the last 60 years, is that machines don't have common sense. They don't seem to be able to accumulate all the background knowledge that's necessary for common sense to emerge. Among other characteristics also that AI systems or machine learning systems today don't have is that most of them are built upon the idea that you compute an output with some sort of finite number of operations from input to output. Of course, you can have recurrent nets that take a longer time, but they're not really used in practice very much, at least not anymore. And there is no, generally in most models, there is no equivalent to reasoning or to planning that certainly a lot of animals and humans are capable of doing. So, I mean, humans and animals understand how the world works. They can predict the consequences of their actions. They can perform chains of reasoning with unlimited number of steps. They can plan complex tasks by decomposing them into sequences of simpler ones. So those are all things that current AI systems really can do. So what is machine learning? So this is the introductory material I'm going to go fast on. So a lot of it is supervised learning. So supervised learning is really sort of the workhorse of practical applications of machine learning today. And the way it works is you build a parameterized function, which is really a program on the computer, but it has lots of parameters that are adjustable in the millions, perhaps in the billions, perhaps in the hundreds of billions today, approaching trillions. And those adjustable parameters are like the knobs on the on the machine somehow, and their configuration determines the input-output function of the system. So if you want to train a learning machine to distinguish images of cars from images of airplanes, you show an image of a car, you run through the system, it produces an output. If the output is car, you do nothing. And the output is something else, then you adjust all of the parameters or a good chunk of them in such a way that the output gets closer to the one you want. And then you keep doing this for millions of examples, and eventually the system settles on a configuration of the parameters that for which the system sort of produces the correct answer for every samples you trained it on, but also, which is the magic of generalization, will produce a decent answer for things you've not trained it on. So new images that are somewhat similar to the ones that the system has been trained on. Mathematically, this is, of course, formulated as an optimization problem where we measure the divergence between the desired output, because we have it in supervised learning, and the actual output produced by the system. And then we figure out, we do an optimization, we perform an optimization procedure to find the configuration of the parameters, which is this vector W, so that the average cost, average over all training samples, is minimized. And generally, this is done using stochastic gradient optimization method. So you take one sample, compute the loss, compute the gradient of the loss, and then update the parameter vector with negative gradient with a step size, or you can do this at the batch level. So that's how it works. It's very simple in principle. And of course, the way we parameterize this function is inspired by neuroscience. There are neural networks, artificial neural networks, which for most of them, it's not all of them, but many of them, essentially each neuron or simulated neuron computes a weighted sum of its inputs with weights that connect neurons with each other. And then the result is passed through a nonlinearity. In modern neural nets, very often, this nonlinearity is what's called a ReLU. It's a half-wave rectifier. And then you stack layers of those linear and nonlinear operations, sometimes with 20, 50, 100 layers. And the W's are the parameters, the knobs that are adjusted by machine learning. To do this, to figure out in which direction and by how much to change each of the parameters, you have to compute this gradient vector of the loss with respect to all the parameters. And this is performed using a practical application of chain rule, essentially. Nothing more sophisticated than this. It's like the vector form of chain rule, if you want. And you can, with this, you can backpropagate signals from the output all the way down to the input and to the parameters, and compute the gradient of the loss function with respect to each of the parameters. That allows you to do take a step in the gradient, in the negative gradient. So nothing super sophisticated there. It's kind of surprising that it took until roughly the mid-80s for people to figure out this could actually be used for machine learning, and it took until the early 2010s, about 10 years ago, for the majority of the community in AI to realize that this was really, really powerful. In particular, if you integrate this in a kind of software framework where all of those backpropagation is done more or less automatically. So you write a function for your network, and automatically the system figures out how to propagate the gradients. So then the next question is, are we going to architecture those neural nets in such a way that are appropriate for particular functions, like let's say visual perception or auditory perception? And of course, there was work, classic work in neuroscience going back to the 50s and 60s, Hubel and Wiesel, about the architecture of the visual cortex, and the idea somehow that fast recognition in the visual cortex is essentially a feed-forward process from the LGN to V1, V2, V4, and the inferotemporal cortex, at least in the ventral pathway. Computer models of this process were proposed in the 1980s, late 70s, actually, also by Kuniko Fukushima, among others, such as the neocognitron, which basically use the idea from Hubel and Wiesel of having neurons that are locally connected, and then having complex cells, the equivalent of complex cells, where the activations of multiple feature detectors, essentially cells, are combined, are aggregated to build a little bit of invariance to variations in positions of the distinguishing features, and then you stack multiple layers. So Fukushima unfortunately didn't have access to backpropagation; it wasn't popularized yet, and so his learning algorithm was somewhat ad hoc and inefficient. What I did in the late 80s was to basically simplify this a lot and build neural nets trained with backprop using kind of the same type of concept. So that's the idea of convolutional nets, where basically it's just recycling ideas from Hubel and Wiesel and then building a neural net that you can train from this. And the result is it's pretty astonishing. So at least in the late 80s, we were pretty astonished by it. It's the fact that you can train those things to recognize simple patterns, and they learn really well, at the time better than competing methods that existed. And they build internal representations of images and other data that seem to be robust to distortions, shifts, size variations, etc. So that was very interesting, and that led to practical applications of neural nets in the 90s. That were like commercially successful even. But then there was a loss of interest in those kind of models until interest was revived by results in speech recognition, image recognition, and later natural language processing. So in particular, in 2012, the use of a large convolutional net by our friends at University of Toronto in Jeff Hinton's group trained on the ImageNet data set that had, over 1 million training samples. And that's really where those neural nets shine. When you have lots of data, you make them big, you make them actually ridiculously oversized, and they turn out to work really well in that case. This posed a puzzle to a lot of statisticians and theoretical machine learning people, because those networks were way bigger than necessary for the task. And the question is, why is it that over-parameterized models of this type still generalize? Why don't they overfit in crazy ways? And this phenomenon is only starting to be understood, really. You may have heard of things like double descent phenomenon and things like that. Okay, so as a result, there's been a huge amount of investment from industry and academia in this kind of research all over the world in the last 10 years or so. And deep learning can do pretty amazing things today, mostly using supervised learning, a little bit using reinforcement learning, mostly for games. And more recently, particularly for natural language processing, using something called self-supervised learning, which I'll talk about more. So things like driving assistance, filtering harmful content on online search engines and social networks, and detecting misinformation, things like that. Environmental monitoring, medicine, medical imaging in particular. This is a short video put together by some of my colleagues at FAIR that shows the capabilities of current computer vision systems. So this is a convolutional net, actually. And the code for this is open source. It's called Detectron2. And that system can detect objects in many categories, put a bounding box around them. It can locate people and figure out in what their pose is. And it can also do something interesting called panoptic instance segmentation, which means it's going to identify every object, draw a mask around every object, and including the background, and basically entirely label the entire image. So this is, so the ultimate task in computer vision, if you want. And progress is extremely fast in this domain, and the amount of publication is so insane that nobody can follow it. Okay, Detectron2, it's open source. Now, what's happened also in recent years is the sort of a deep learning revolution since around 2014-15 in natural language processing, and that has completely exploded in the last 4 or 5 years with what's called self-supervised learning. So self-supervised learning is the idea that you train a system not for a specific task, but for a sort of generic prediction task of essentially filling in the blanks. So the way you pre-train a natural language processing system is that you show it a string of words extracted from a text corpus, and you remove some of the words, maybe 10 or 15% of them, and you train some gigantic neural net to predict the words that are missing. In the process of doing so, the neural net learns an internal representation of text that basically contains a lot of what is needed for syntax, semantics, and everything. It basically understands at some superficial level what the underlying reality is. But of course, it's not connected to any sort of real underlying reality. But those systems are really amazing in the sense that they can be used once they've been pre-trained. They can be fine-tuned for things like hate speech detection, all kinds of natural language processing tasks, dialogue systems, as well as generating text, as well as translation. So this is a project, again, by some of my colleagues at FAIR called No Language Left Behind. And this is a large neural net that can translate between 200 languages in any direction, any of the 40,000 directions. But the number of parallel sentences only covers 2,400 of those language directions. And so it's only a partial data set, if you want. It's 18 billion pairs of sentences, but most pairs only have 1 million sentence pairs. And with pre-training a system like this and then fine-tuning it to do translation, it's a relatively small model by today's standard, 54 billion parameters. It can translate 200 languages in any direction fairly accurately. 200 languages is a lot. There's a lot of languages here where, I don't know about you, but I have no idea where they are or where they come from, but that covers a large proportion of speakers in the world. This is really important for not just for erasing cultural barriers, but also to do things like content moderation in all world languages. There are countries in the world that speak some of those languages where there are ethnic or religious rivalries, and people use social networks to basically fire themselves up against the other communities, and you have to be able to detect those things. It's very hard. Okay, applications of deep learning to science, particularly in neuroscience, but all kinds of science, things like genomics and biochemistry with protein folding and protein design. In neuroscience, a lot of work on trying to use convolutional nets as a model of what goes on in the visual cortex. Classic work, but now by Yann and DiCarlo a few years ago on trying to sort of correlate those two things. And more recent work, or actually not that more recent, are trying to correlate really what the layers in a convolutional net do relative to what area in the brain they would explain the variance of. And clearly there is some correlation between the sort of layer hierarchy in the convolutional net and the sort of V1, V2, V4 IT hierarchy. Similar work, more recent one by some of my colleagues here, Charlotte Cochuteux and Grandfort and Jean-Amy King. This is Jean-Amy King's group, his joint appointment between FAIR and ENS. And this is using kind of similar techniques, but trying to understand or explain what we observe in fMRI when people are listening to a story and then trying to understand the story, and then trying to correlate this with the activation that is observed in a large language model like GPT-2 in this case. And sort of using this, there's some non-trivial correlation between the degree of understanding that a person has of a story and the correlation of the brain activity with what is observed in the model neural net. Now those neural nets are nowhere near good enough to really be a good model of what goes on. Sorry about that. But it's still kind of interesting to see that there is this sort of hierarchical relationship. This is a very recent paper that basically just appeared in Nature. Reinforcement learning. So a few people for a while have been excited about the fact that reinforcement learning does not require human labeling, unlike supervised learning, so which would be a better model of human and animal learning. But it's incredibly inefficient in terms of trials and samples. And so it only works well in simulated environment, but so far it really doesn't work in natural environments unless you can collect lots and lots and lots of data. So like in a search engine or something like that. So there's been some success, but just to give you an example, to get let's say the Alpha Star system produced by DeepMind a few years ago that plays the StarCraft strategy game. This system requires about 200 years of equivalent real-time play to reach the level of a human on one particular type of game. Clearly, those methods are nowhere near the kind of performance that we observe in humans and animals. So obviously the answer to this is that humans use their background knowledge, right? But it's a big question because we'd like to be able to train cars to drive themselves, and obviously any teenager can learn to drive a car in about 20 hours of practice without causing any accident. And with reinforcement learning, we cannot train a car to drive itself. Even in simulation, it's very long, because a car doesn't have any background knowledge about the world. It doesn't know that if it drives near a cliff and it turns the wheel to the right, it's going to run off a cliff, and then something bad is going to happen. It has to try it multiple times before it realizes it's bad, and then it has to try it multiple times again before it figures out how not to do it, and then it has to do it again for another cliff because it doesn't look the same. So obviously this is not there's something missing, and and the question is what is it? So we're not going to get to reproduce human and animal learning just by with supervised and reinforcement learning. That's pretty clear. So how do humans and animals learn so quickly? Now, one thing that happens with humans, but also with animals, is that babies seem to acquire a lot of background knowledge about the world in the first few months of life, mostly by observation. So babies are kind of helpless. They can't really influence the world other than, kind of moving their limbs. But in the first 3 months, at least, they really can't affect the rest of the world. And so they learn a lot about the world just by observing. They learn to do things like distinguishing animate objects from inanimate objects. They learn object permanence. They learn things like stability and rigidity and things like that. They certainly learn natural categories without being told the name of things, and animals do this too, right? So a lot of this is non-social and non-linguistic. Certainly in a lot of animals, it's like that. And then it takes about 9 months to learn about intuitive physics like gravity, inertia, conservation of momentum, things of that type. So how do we learn all this? How do even baby animals learn all this? If you show a 6 months baby the scenario here at the bottom where you push a little cart off of a platform and it appears to float in the air, a 6-month-old baby will barely pay attention to it. A 10-month-old baby will go like the little girl here at the bottom because she has learned that objects that are not supported are supposed to fall, and this object is not falling, so her model of the world is being violated, and she's paying attention because she thinks she might learn something from it. So that, what kind of learning is taking place when we do this? And perhaps the accumulation of background knowledge that occurs during this sort of type of training constitutes the basis of what we call common sense. And I stole this chart from Emmanuel Dupuy, by the way. So there's really, I would list 3 main challenges for AI and machine learning. The first one is learning representations of the world, as well as predictive models of the world, just from data, not without any labeling, without any reinforcement or reward. And that's basically what I'm going to argue is what self-supervised learning is. And self-supervised learning really is kind of learning dependencies between the inputs and learning to fill in the blanks. I'll come back to this. The second challenge is learning to reason. So a lot of what neural nets do right now are akin to Daniel Kahneman's system 1. So basically kind of reactive subconscious tasks. But then when it comes to planning and reasoning, this is more like system 2. It requires the entire focus of our prefrontal cortex and kind of think about predicting the consequences of our actions. Current neural nets, current architectures really don't do this, at least not well. There's some robotic systems that do this, but I'll come back to that. And so that is a form of reasoning and planning, and the challenge is to make reasoning compatible with learning, basically. And then there is learning to plan complex action sequences, which is really kind of a sub-problem of problem 2. I came up with this analogy several years ago that said when you train a system using reinforcement learning, you are only giving it feedback that is very weak. You're telling it, your answer was good or bad once in a while, and the amount of information that contained in this feedback is very, very small. As a result, the number of trials that the machine has to do to learn anything is very large. In supervised learning, the supervisory signal gives a bit more information per sample to the system. It's 10 to a few thousand bits per sample or something like that. But it has to be provided by humans, so it's not that great. It's never in really large quantity. Self-supervised learning would be more like, here is a piece of input, predict the rest of the input that you're not currently seeing. And there, the amount of supervisory signal you're getting is enormous. And so presumably you can learn a lot about the world using this type of learning. And so that led me to this analogy that if intelligence or learning is some sort of cake, the bulk of the cake really is self-supervised learning, and then the icing on the cake is supervised learning, and the cherry on the cake is reinforcement learning. And of course, that doesn't make my friends who work on reinforcement learning particularly happy. And this is not to say that reinforcement learning is bad. There are situations where you have absolutely no choice, but basically the philosophy is it's so inefficient that the use of it should be minimized. Okay, so what I'm going to do now is present a proposal for an architecture. And I must say it's a proposal. I haven't built it, or at least not completely. And this proposal is a way to basically address those three challenges I was talking about. And it's what people used to call a cognitive architecture, right? So it's basically built around this green module here, which is not randomly placed on top of the prefrontal cortex here, called the world model. And what the world model is basically a module that allows the agent to predict what's going to happen in the world, perhaps as a consequence of its actions, and therefore can be used for planning. There is a cost, again, non-randomly placed around the basal ganglia. And the cost is composed of two submodules: the intrinsic cost, which is sort of a hardwired set of objectives that basically determine the nature of the agent. So these are things that, you know, think of this as, you know, the pain and pleasure circuits in the brain. And then a critic, which is sort of a trainable part of the cost or configurable part of the cost that basically allows the system to focus on the task by optimizing this cost. The actor is a module that, think of it as the premotor cortex or something like that, that essentially tries to figure out a sequence of actions. Imagine a sequence of action that, given the prediction given by the world model, will optimize the cost, minimize the cost. Okay, and then the actor can also produce actions through the motor cortex. Of course, upstream of this, you need to have a perception module that basically gives the system an estimate of the state of the world, perhaps combined with some sort of memory. Okay, so we have kind of all the modules in this system here. Excuse me. And we can use it in two different ways. One would be mode one, assimilable to Kahneman's system one, where we observe a set of percepts from the world, running through the encoder, which gives us an idea of the state of the world, perhaps running through a cost function, but that's not necessary. And then just running through what could be called a policy network in the actor that produces an action directly. So this would be sort of subconscious reactive actions where we don't need to think about it, we don't need to plan. And then mode two, which is more sort of deliberate conscious planning, if you want, where we observe the state of the world, again, extract a representation of the state of the world using the perceptual module, compute this the cost of this of the state, and then run that repeatedly through our world model. So this predictor here is a world model. And what the world model does is that, given an imagined state of the world, S of t, and given an action that we might be taking, that we're imagining taking, the system predicts the next state of the world, all right? And then feeds that to the cost function that computes the cost of that state. And then we do this multiple times for a whole episode. Now, the actor can search for, using optimization methods, can search for a sequence of actions that will minimize the overall objective averaged over the episode, over the trajectory, using using the world model as its predictions. Now, the world model may not be completely deterministic because the world is not entirely deterministic. So I'll come back how to address this later. For now, we'll view it as deterministic, or kind of swipe this problem under the rug. And this type of this way of using a predictive model and a cost is really completely equivalent to what classical optimal control people do in what's called model predictive control. Except that here, this model of the world is going to be learned. It's going to be, our how are we going to learn it? And so that's where self-supervised learning comes in. That's how we're going to learn the world model. There is a way to compile a sort of mode 2 skill into a mode 1. So if we infer an optimal sequence of actions in mode 2, we can use those actions as targets to train a policy, so that next time around, when we encounter the same situation, we can just apply the policy and take the action directly without having to think about it. Okay. So the cost function, as I said, is composed of two submodules, intrinsic cost, which is immutable. So this is, pain and pleasure, hunger, things like that. And perhaps a few intrinsic costs that kind of drive the systems towards learning tasks that skills that we know are useful in the future. And then a trainable part of the cost, which could be seen as a critic, actually, that tries to predict long-term values of the intrinsic costs in advance, or constitute sort of temporary costs that the system needs to pay attention to. So for training the critic, we would need some sort of short-term memory that remembers states and corresponding intrinsic cost values, so that we feed the state to our critic, and then a few time steps down the line, we know what the eventual cost of the intrinsic cost was, and we use this as a target to train our critic, or some combination of future values. This is classic stuff in reinforcement learning. Okay, so how do we build and train the world model? Because really that's where the big question resides at the moment. That's the part that we don't know how to build. So the problem is the world is not completely deterministic. So if I build a neural net, which is a deterministic function, to make a single prediction, and there are multiple possible predictions, if I put a pen on the table, I let it go, it may fall in different directions every time, right? And so if I ask the system to make one single prediction, it's going to have to predict some sort of average of all the potential outcomes, and that's not a good prediction. So I have to be able to handle uncertainty in prediction. Here's another example here. This is a top-down view of a highway, and this is a recorded video, and this is what a convolutional net trained to predict those videos produces, and it's very blurry predictions. Same here at the top, you see this little girl. The first 4 frames of the video are observed, and the last 2 are predicted by a convolutional net, and it makes blurry prediction because it can't really predict exactly what's going to happen. So it predicts some sort of blurry mess of all the potential outcomes. So my solution to handling uncertainty is something called a JEPA, Joint Embedding Predictive Architecture. But before that, I'm going to talk about self-supervised learning. So self-supervised learning would be used to train a system with unlabeled data to learn representations of the world, but also to predict what's going to happen so that we can use it as a predictive world model. Okay, so let's say we have, a chunk of video. We feed the system with the initial segment of that video, and we hide the remainder, and then we ask the system to predict the remainder and of the video, and the system is supposed to train itself to kind of tell us to what extent the continuation of that video is compatible with the initial segment that we saw. And that prediction is not necessarily in the future. It could be in the past. It could be left from right. It could be anything. It could be left eye from right eye. Anything. Predict everything from everything, essentially, fill in the blanks. And that can be used for learning hierarchical representations or forward model of the world. But how do we represent uncertainty and multimodality in the prediction? So here I'm proposing, and this is the slightly more theoretical part of the talk, I'm proposing something called energy-based models. So of course, the normal instinct for a machine learning person or a statistician is to say, well, we're just going to use probabilistic modeling, right? Obviously, there is a distribution of probabilities of what can happen after a particular video clip, and I'm going to just model that distribution, do a conditional density modeling. And of course, the problem with this is that it's intractable. We don't know how to model distributions in high-dimensional continuous spaces, or at least not normalized distributions. So what I'm proposing here is something called energy-based models. So it's kind of a weakened version, if you want, of uncertainty modeling, which is not probabilistic. And basically it says, if I want to capture the dependency between 2 variables, x and y, I need an energy function f of xy that will give me low values when y is compatible with x, and higher values when y is not compatible with x, okay? So if y is a good continuation of the video clip x, then f of xy is small, let's say 0. And if it's not a good continuation, then it's larger. So yeah, here is a kind of depiction of this, where x and y would be here scalar variables. And the black dots would be the training samples. And my model would need to give low energy to those training samples and then higher energies to everything else that is not observed. And that's the second part of giving higher energy to everything else that is complicated from the point of view of learning. So basically, we're turning an explicit function into an implicit function. where the dependency between X and Y is captured through an implicit function. The advantage of this, of course, is that now we can have multimodal dependencies between X and Y. So for a given X, there can be multiple Ys that have low energy, and that's a way to represent uncertainty. We can, of course, do inference for a given X by finding a Y that gives us the lowest energy, for example. It may not be practical in all cases, but something we can do. We can, in some cases, transform an energy-based model into a probabilistic one by basically taking exponential minus and normalizing. This is a classical Gibbs formula, right? That comes from statistical physics, where P of Y given X is e to the minus some constant, the energy, divided by a normalization constant, the partition function. The problem, of course, here is that this integral may not converge, or even if it converges, it may not be tractable. So we may not be able to compute it. So what I'm arguing for here is basically, let's drop this whole idea that somehow the energy is the logarithm of some probabilistic, some density. And let's just work with the energy directly. And there's nothing wrong with that. Energy-based models can have latent variables. So it's possible to define an energy f of xy as being the minimum over z of some more elementary energy function, E of xyz. Okay, so you have an energy function of 3 variables. You minimize over the third variable, and what you're left with is an energy function that only depends on the 2 variables, x and y. That's important for a lot of applications. I'll come back to this. So how do we train an energy-based model? So we can do maximum likelihood because we're not in a probabilistic framework. And the main issue that we have to deal with is the collapse problem. So we can, of course, easily show a sample so our energy model is going to be some neural net, okay, that has 2 inputs and a single scalar output. And we're going to show it pairs of inputs, which are going to be those blue spheres here, those blue dots. Okay, and what we can easily do is make sure that the energy that our model gives to those blue dots is small by just putting down on them, right? So we're going to, by gradient descent, we're going to compute the gradient of the energy for a training sample with respect to the parameters of the energy model, do a step in gradient descent, and as a result, we're going to make the energy of all of our training samples small. But the problem with this is that we might end up with a collapsed energy function where all the energy of everything is small. And that doesn't give us a good model of the dependency between X and Y here. What we need to do is have an explicit mechanism that makes sure the energy outside of the manifold of data is higher. Okay, so if we had a probabilistic model, maximum likelihood would do that because it would tell us, like, you only have a finite amount of probability to push around. So if you give high probability to something, you have to give low probability to the rest. But here we have this is not the case. So here there are 2 classes of methods to train energy-based model. One is contrastive methods. Contrastive method consists in generating contrastive points, those green points that are flashing. And then, so they would be sort of outside the manifold data, and we would push their energy up. Okay, so push down on the data points and then push up on those green points. That's contrastive methods. In high dimension, this may not work really efficiently because we may need an exponentially growing number of green points as the dimension of the space grows. And then there are regularized methods, and regularized methods basically consist in minimizing the volume of space that can take low energy, so that if you push down the energy of the training samples, the rest will have to go up because there is only a finite volume of low energy stuff to go around. I only know those 2 categories of method. If you have other ideas, I'm all ears. And then, classical architectures of neural nets can, some of them can collapse and some of them cannot. So a sort of regression system, deterministic function, a neural net with multiple layers that makes a single prediction and has a cost function, like what is typically used in supervised learning, that cannot collapse because for a given X, for any Y, there is only one single output that can take low energy. And so this does not handle multimodality, does not handle uncertainty, but it does not collapse. There's generative models that are non-deterministic, and what that means is that they have a latent variable. So as you vary the latent variable over a set, the prediction varies over a set. And the energy of a pair, XY, is basically the the prediction error for the value of the latent variable that minimizes this energy. So find the value of the latent variable that makes the prediction as close as possible to the output, the observed output, and then measure that divergence, and that's your energy function. And there it can collapse if the latent variable is too powerful. If it, for example, has the same dimension as the output variable, then for any value of y, there is going to be a value of z that makes the prediction error 0. And what that means is that any value of y will have 0 energy, and that means your model is collapsed. The way to fix this is to limit the domain of z, or to limit the information content of the z variable, so that the volume of stuff that can take low energy is limited. So that would be a regularized method. Then autoencoders can collapse. Let me not go through this. And then joint embedding architecture, which is what I'm going to spend the rest of the talk about. You run both X and Y through encoders, and then you measure some sort of distance between the two representations here. And so for pairs of X and Y that are compatible, you want to make this distance small. And for other pairs, you want to make sure it's high. And you can do this with contrastive methods or perhaps with regularized methods. This can obviously collapse because the encoders can choose to completely ignore X and Y and set Sx and Xy to equal values and that are constant. And then your energy is 0 all the time. So again, you get a collapse. Okay, so it's all about collapse prevention, either through contrastive or regularized methods. So I made a list here. I don't expect you to read all this, but basically you can classify every classical method, whether it's supervised or unsupervised learning, whether it's probabilistic or not, into whether they are contrastive or non-contrastive, or regularized or architectural. So anything that is doing maximum likelihood with Monte Carlo or Markov-chain Monte Carlo methods is actually a contrastive method. Contrastive divergence, of course, is contrastive metric learning and Siamese nets in the classical way. Noise contrastive estimation, GANs are contrastive. Denoising autoencoders and max autoencoders are also special cases of contrastive methods. This is the method that is being so successful in natural language processing these days. And then in non-contrastive method, you have things that are familiar to theoretical neuroscientists, like sparse coding, like Holzhausen-Field, 1997, sparse autoencoders, variational autoencoders, and various other methods, and new methods that I will talk about here, Barlow twins and Vic Reg. So contrastive method, let me go quickly on this because I'm actually going to argue against them. So there's been a lot of them over several decades. And they all consist in sort of, generating contrastive points and then pushing up their energy by feeding that to various loss functions. I'm not going to go through the details of this. Many of those techniques were developed in the context of speech recognition for discriminative training. But some of them are kind of, coming back to the fore because contrastive methods are being used. And so this is the way contrastive methods, particularly denoising autoencoders, are used in natural language processing. Take a piece of text, remove some of the words, and train some gigantic neural net to predict the words that are missing. And then once this is trained, use the internal representation as input to a downstream supervised task. So this works really well for NLP. It's become completely standard. It's revolutionized NLP in the last 4 years, since 2018. Although there were kind of early work with sort of similar flavor in 2011 or so, in fact, earlier. So an obvious idea is, why don't we use this for images as well? Take an image, block some of the areas of it, and then train some giant neural net to predict the missing parts. And this works to some extent in the sense that it actually fills up the image with things that make sense. But then when you use the internal representation as input to a subsequent task, for example, object recognition, it doesn't work that well. It's not that great. And so what works is joint embedding architectures. So joint embedding architectures are the thing on the right here. So on the left is a generative architecture, which directly produces a prediction of Y. A joint embedding architecture, which I already talked about. You embed both, you encode both X and Y. And in the process of encoding Y, the encoder here may have invariance properties. And what that means is that when Y varies over a set that leaves SY invariant, all of those values of Y will have the same energy, okay? So if you have a pair XY that has 0 energy, and you vary Y within the invariant set of the encoder, all of those Ys will have 0 energy. And what that means is that this system can represent multimodal dependencies by basically eliminating irrelevant information variations from the Y variable. This is called a JEPA, joint embedding predictive architecture, because there's a predictor here that tries to predict the representation of Y from the representation of X. In fact, if you want the system to be completely general, you need to have a latent variable in the predictor that allows the prediction of representation of Y from that of X to have some uncertainty in it. Okay, so that's the full JEPA, joint embedding predictive architecture. The question is, how do we train this? So we're going to train this using non-contrastive regularized methods. And what you have to realize is JEPA tries to find a trade-off between two things. The first thing is maximizing the information content that SX has on X and SY has on Y, so that they are sort of maximally representative of what goes on in X and Y. But at the same time, predict SY from SX, and therefore, essentially, this will drive the system to eliminate information about X and Y that, or particularly about Y, that is not predictable, that is completely non-predictable, like noise, like random motion of things in a video, things like that. And it will find a trade-off between them. So let me skip the contrastive method for lack of time, although they are kind of popular at the time and they work really well for certain applications like speech recognition. Let me directly jump to regularized methods. So we're going to try to find a criterion that minimizes the volume of stuff that can take low energy. And we're familiar with this in neuroscience, in computational neuroscience, with things like sparse coding. So sparse coding is a latent variable model that is decoder only. So you have a latent variable that is regularized, in this case with an L1 norm, that goes through a predictor, which in this case is a linear decoder. And then we measure the reconstruction error between an observed image patch, let's say, and the reconstruction. And then we can train the system using gradient descent, all the while minimizing the energy with respect to Z for every sample. And of course, we know since ultrasound in field that this will learn V1-like receptive fields in the decoder. We can train sparse autoencoders with similar ideas. So again, with the sparsity criterion, this is some work from my lab from 12 years ago or so, where you can learn very highly diverse feature detectors in an encoder or a decoder. So this is an autoencoder that has an encoder and a decoder with a sparsity criterion in the center in the representation. And this works quite well. But I'm going to argue for this type of JEPA architecture. And basically, the criterion we're going to use to train this is one in which we have some measure of the information content of SX, and we're going to maximize that. Some measure of the information content of SY, and we're going to maximize that as well. Okay. Then the prediction error, we're going to minimize that. And then the information content of Z, and we're going to minimize that, because if we don't minimize this system can collapse again, for the same reason that a generative model with a powerful latent variable can collapse. So that would be how a JEPA is trained. And a particular instance of this is called VICREG. So that means variance, invariance, covariance regularization. This is a paper that was published at iClear this year by Adrien Barne, who is a student with me at FAIR Paris, Jean Ponce, and myself. And there are sort of similar algorithms from Yima's group at Berkeley, one thing called MCR squared, for example. VICREG actually was sort of a tweak on the previous algorithm that we published a year before called Barlow twins. And it's inspired by classic work by Horace Barlow on sort of, efficient coding, basically. So the criterion we use here is we take SX and we fit it to two cost functions that whose purpose is to make the covariance matrix of the SX activation vectors over a batch of samples as close to the identity as possible. So this is done by having a hinge loss on the standard deviation of each of the components. and then having a term of the covariance off-diagonal covariance terms that push them to 0. Okay, so we're trying to make the covariance matrix of Sx as close to 0 as possible. So this will have the effect of making each component of the representation of Sx have non-zero variance, and also make them decorrelated. We play a trick here, which is that we also run this vector through an expander, which is a trainable neural net, and apply the same criteria. And this will have the effect of making the components of Sx actually pairwise independent, not just decorrelated. So we sort of train this this way using a square error here. In the experiments I'll show, we don't have a latent variable here. So and we can train this, for example, on ImageNet. So you take an image, distort it a little bit, and those are your x and y's, and that constitutes a positive sample. And then you do this for all the examples on ImageNet with all kinds of distortions, and then you chop off the last layer, the predictor, basically. You use the representation as input to a classification system that you train supervised, and these are the performance you get. And VGREG works quite well compared to other methods. So these are all kinds of methods that are self-supervised for images. And there is a lot of progress that is happening extremely quickly. Those results are actually already obsolete with other methods that have produced better results. There is only a slight issue with this, which is that those techniques for training a vision system require a lot of knowledge about the image to do distortions and things like that. And so what people are after these days is techniques that only require masking. So essentially you show an image, two images for X and Y, but they have sort of different masked versions of the same image, for example, or masked pieces of video. So this is what people are working on at the moment. And it's starting to work. Yes. Yeah. I'm gonna.
If we want to take some question, take into account the fact that you have some boundary limits. So
correct. I'm actually fairly flexible, but we'll. I'm taking 3 minutes to end. Okay, so. So a big advantage of those JEPA architecture is that we could stack them, and so train hierarchical JEPAs. And a big advantage of this is perhaps we can use this to train world models, predictive world models, that will allow a system to kind of make long-term predictions. So here is how this could be used. So look at this predictor and this encoder; they are the same as this encoder and this predictor. So we take an X running through the encoder, get a low-level abstract representation of the state of the world, run it through the predictor for a couple of steps, and then we have actions here that may determine the next state of the world. Okay, but then we have a higher level here, and this higher level basically extracts a higher, more abstract representation of the state of the world and makes longer-term predictions. So each predictor here predicts not at the next time step, but maybe some longer term time in the future. So let's say here we want to go from New York to Paris, and that cost function is how far we are from Paris. The first action will be, am I near the airport in New York? And the second one would be, have I landed in Paris? And then that will determine a cost function for the next layer down, which is, how close am I to the airport? And then, those actions would be, am I taking a taxi? And, is the taxi taking me to the airport? Things like that, right? So you can imagine decomposing a complex task into simpler and simpler one, all the way down to millisecond by millisecond muscle control using this kind of hierarchical architecture, where a particular level determines a cost function for the lower level. You would have to have latent variables to account for the uncertainty in the world, but I'm not going to go into the details. So coming to the conclusion, self-supervised learning is really what's needed for the next step in autonomous AI systems, and how precisely to make those JEPA architecture work as world models is not entirely worked out. To handle uncertainty, we need these JEPA architectures, as well as the energy-based model framework. We need a system to learn world models mostly from observations. Of course, they will have to do some sort of interaction and reinforcement learning, but we need to minimize that as much as possible. Reasoning and planning basically is finding those optimal sequence of actions to arrive at a goal. So there's no need for symbol or logic. It's basically vectors and continuous functions. Now, there's one piece I didn't talk about, which is this mysterious configurator here. And the role of this would be to configure the rest of the system to focus on a particular task. So it would configure the cost for a particular task, configure the world model for a task, perhaps even configure the perception system for a task. I don't know, you're looking for a tool in a drawer, you're kind of configuring your perceptual system for that, etc. And perhaps the reason why we think that we have consciousness is because we have a single world model in our head, which basically constrained us to only accomplish a single conscious task at any one time, because we have a single engine, and it has to be configured for the task at hand. So the configurator sort of basically kind of has to observe the rest of the world and have the rest of the system of the agent and have a model of it. And so that maybe is a crazy kind of speculation that maybe this is what gives us the illusion of consciousness. And I'm done. Thank you very much.